Right. Good morning, everybody. We continue our tour of unsupervised learning. I would like to start today with kernel density estimation and later move on to a particular type of clustering algorithm. So as the name implies, the idea of kernel density estimation is to well estimate densities. So in one dimension, let's say we are given a couple of samples, and we assume that these samples have been drawn from some underlying probability distribution, and we would like to know what that looks like. And well, it's probably going to have some more probability here and some less there and little or no question mark out there. So we would like from these samples to go to something like that. And well, why would one possibly want something like that? Can you please close the door quietly, if you two, if you must come late? Thanks. And there's a rear entrance, okay? Thanks. So, all right, we'll talk about that later. Why are we interested in density estimation? An important application in physics is to detect outliers. So if we have a good idea of what the background distribution looks like, then we can use that to estimate the density. And if we then find outlying samples, those with a very low probability, those might be the ones that hide new physics. Or sometimes we want to generate samples. Again, with a view to, this is also used with a view to outlier detection. There are more modern methods for all of these, of course. For sample generation, we would nowadays use something like diffusion models. For example, which we will look at later in the semester. Or for density estimation in general, nowadays one would probably, if we want to do it with a neural network, use so-called flow-based methods. That flow-based methods would relate this space to another space where the density becomes very simple. So in that other space, the density would, for example, be Gaussian, and then a neural network distorts this space so as to model these kind of samples well. Also something we can discuss later in the semester. But it's good to look at the baseline model first, before we go to the neural network formulations. And kernel density estimation is a very, that was good. Kernel density estimation is a meaningful way to do that. It also happens to be a way which is motivated by a physics model, namely it comes from the heat equation. What the heat equation tells us is that if we deposit, for example, with a laser, let's pretend that this is a metal bar here. And if we deposit heat in a few locations, for example, with a laser, let's say like here and here and there, then we can write the Cauchy problem, and we find that there is a temporal evolution happening which corresponds to convolving these peaks with Gaussians, whose width depends on how long the diffusion process has been going on. So what I'm drawing here is maybe for t equals 1, and then for t equals 2, these Gaussians become wider. So they start to blur these features here. That would be t equals 2. And then as we go to t equals infinity, everything becomes perfectly smooth. All right, and if you want to look up the derivation of where this comes from. So this is, by the way, where Fourier, that's the problem in which Fourier invented the Fourier transform in the first place. There is a nice discussion on math.stackexchange. You can, of course, find it in textbooks also, but there's a nice summary here. And I'll just give you the number. All right. Good. So the heat equation tells us we take these initial sources and we diffuse them with the Gaussian, and we can do something similar now for the kernel density estimation. So we start with the density E hat of x, and we have a number of initial. So here I said this was the heat we deposited, or we have a couple of samples numbered from 1 to n. Those are located at positions xi, and then we convolve this here with a kernel that has a parameter. It's width w, and so this is a set of Diracs at these various locations xi, and so the summation we could take in front of the integral, and the integral of a delta that simplifies the whole thing. So what we find is that this is 1 over n. All right, and these kernels here. These kernels k, they will integrate to, they should be normalized. And not always, but usually we choose them to be non-negative. In theory, it is possible to choose a kernel which does have negative lobes, and that can reduce bias, but the typical choice is to have them non-negative. And these kernels, they can now have a variety of shapes. So a bad one would be the box kernel here. Because I say bad because if we now take many of these displaced box kernels, we will get a density estimate that looks very jagged. Yeah, we will get. I'm going back to this picture here. If we use a box kernel of a small width, let's say we use this width here, and we convolve it with these points, well, we will get something that looks like so, and it goes on and on. So it's not a nice, smooth density estimate which we get out. We wouldn't really believe having all these tiny peaks here. We can, of course, choose a wider kernel. Then many local minima will disappear, but it will still be a piecewise constant, a very jagged estimator. So it is typical to use something which is smoother. So, for example, a triangular kernel can be used, or, for example, a B-spline can be used. It starts to look like a Gaussian, except it has zero support beyond its cutoff. We can, of course, use actual Gaussians also. Maybe switching colors, we can use actual Gaussians. Or in the context of density estimation, a popular one is the Epanechnikov kernel, which is a truncated parabola. All right, so we have this choice of kernels, and different kernels will give us different density estimates. All right, and now one question we can ask is, what is the expected if I draw samples repeatedly? So let's say from the same distribution, I have drawn samples again. This is another sample that I've drawn, or maybe I find this. So as I draw multiple samples from my underlying distribution, I will get a different kernel density estimate each and every time. And we can ask, what will these kernel density estimates look like on average? Yeah, what do we expect them to look like? All right, and for this, what we need is the expected estimate. And this expectation operator, I would like to talk about a little bit. You have all seen it, of course, but I wanted to repeat what we know about random variables. Because to start with, random variables, the name for them has been really fully chosen. So, sounds random, but random variables are in fact deterministic functions. And they are a deterministic function from a set space. I'm now assuming that it contains discrete outcomes. So we have the space here of possible outcomes. And then the random variable gives me a mapping from specific outcomes to particular realizations. And this mapping need not be invertible. So in particular, we can have here different outcomes that map to the identical numerical value. And when we say random variable, then this mapping here is from this space of outcomes to just a single real number. And in this space here, we can also have events. Events are subsets of outcomes. For example, these taken here together, that would be an event. All right, and then a statistician very formally would write that the probability of here, if this is a discrete set of possible realizations, then the probability of any single realization would be the probability of, so we would count what's the probability of the outcomes that map to this particular realization. Yeah, so this would be here the probability of the set of outcomes such that capital X now is the random variable associated with realization small x, such that the random variable x of w equals x. Okay, or another shorthand is to say that this probability here. Yeah, so the capital letter is always the random variable, and the small letter is the realization. And then we have the definition of the expectation. The expectation of some random variable x, if it's continuous, would be the integral of p of x times x dx. And if it's discrete, we could write it like so, or we could write it like so. Okay, that's the expectation, and then it has a number of important properties. So the expectation of a function of a random variable is the integral of r of x, p of x dx in the continuous setting. And it is linear. So the expectation of ax plus b would be a times the expectation of x plus b. And expectations of random variables add up only if they're independent. So, for example, when we have a case where that would not be true is if we have negative correlations. If we have a random variable x1 and x2, and they're negatively correlated, then all right, this is a bad example because the expectation of the first one was 0 and the second one was 0, and then their sum is also 0. Bad example, but if I shift the origin, that would be a better example, where one would see that this does not hold if the random variables are not. Oh damn! I'm talking nonsense. Anybody noticed? No? Wrong statement. I was thinking about the variance, and this is a wrong statement. This is just true, full stop. Okay? I'm sorry about this. So this is always true even when they are dependent. And I noticed when I was now trying to construct a counterexample in my head. All right. Good. Now, these are, so far we talked about scalar random values, but there are also more general sets of objects which we can study when we look at stochastic processes. So there are more general entities would be, for example, random vectors, vectors of random variables, or we can have random sequences. And in random sequences, I'm giving you two different realizations here. Okay, the axis here, we can index this, for example, with time. And if we now look at just a single point in time, then the possible values that we could observe, so if we condition on a single point in time, this would be a random variable. But if we look instead at one of these time series, then this is what we would call a random sequence. And if we again want to have this image here of the event space with possible outcomes, then now each outcome would map to one particular random sequence. And of course, we have many outcomes and many possible random sequences. So that's discrete. And then there's also continuous version thereof, which would be a stochastic process. Running out of space here, but we would again have space or a time dimension, and each single realization would now be some, not necessarily smooth, but some continuous function here of time. So my index set in the time domain or in the space domain now becomes continuous. All right. And then there are still other properties. For example, we can also have random trees, random graphs, and so on. These are of much interest in recent machine learning. We can have the same with more than one dimension. Then, so we can have not just time series, but we can have really surfaces in as many dimensions as we want. Okay, and equipped with this, we can now return here to the question of the kernel density estimation. So if we want to ask, so I'm again sketching, what are we looking at? Let's say we have drawn couple of samples from the same underlying distribution. We get out a kernel density estimate each time. So we pick one of those kernels. Maybe we pick here this nice bi-weight kernel, and we get some estimate. But those estimates will never look quite the same, yeah, because the underlying samples are different. And now we want to know what's the expectation of these estimates at one given point in space. Yeah? So the expected value of this kernel density estimate. And assuming that we have drawn n samples, we're taking the expectation with respect to x1, x2, and so on, up to xn. We can insert the formula for the kernel density estimate. And now we have here a sum of terms, but each term depends only on one of the random variables. And then it is sufficient to take the expectation only with respect to that one random variable. So we get sum over 1 to n, and then the expectation only with respect to the ith random variable. Okay, and now if we assume that all of these samples follow the same distribution, then it is really sufficient to pick one of them. For example, the first one. And okay, I'm doing this now very detailed. Yeah, we have I equals 1 to n. But now we only take the expectation with respect to the first random variable. And now we have this thing n times, and this will cancel. So we have the expectation of k of x minus x1. And now we use the definition of the expectation function here. And it's this case. Yeah, we have the expectation of a function of a random variable. And so what we have is the integral here of k of x minus x1 times p of x1 dx1. Okay, here we have x minus x1, here we have plus x1, so this whole thing is a convolution. Okay, so what we find overall, we started up here. The expected value of the density estimate is a convolution of the true underlying density with the shape of the kernel. Put that in words. expectation of the kernel density estimate is the true density convolved with the kernel that we're using. And this means in particular if our density, if the true underlying density has some very sharp features, so maybe the true underlying density looks like so, using kernel density estimation, we're never going to recover this. If we use as a kernel now, let's say here the bi-weight kernel, then given enough samples, we might obtain something that looks pretty good up to here. But then at this point, it will just blur over this feature in the underlying density. So what we get is some kind of blurring effect. And this blurring effect is, as we make our kernel wider, this blurring effect becomes stronger. All right, so if we only look at this, it sounds like the narrower the kernel, the better. But of course, there's a trade-off involved. So what happens if we make our kernel very, very narrow? Yeah. Exactly, yes. So if I make my kernel very narrow in the limit of making it infinitely thin, I will just get a spike at every single observation. That's not a very useful density estimate. Yeah? And so the sweet spot is somewhere in between. Yeah? And now the statisticians, so here blurring, this suggests this would suggest that narrow kernels are good, but on the other hand, we will get these density estimates that are very spiky and that look very different one from the other. So if I use a very spiky estimate, well, in this sample here, I will get 2 spikes, and at that sample, I will get 3 spikes. Yeah? So they look qualitatively different. And so what one can look at across this set here of density estimations is not just their expectation, but also their variance. So the variance means how much does it, what is the spread around this expected value. And this, this spread around the expected value will grow if we make the kernel too narrow. So if we choose the kernel too wide, we get an over-smoothing effect. And if we use the kernel too narrow, we will get a very noisy or a high variance estimate. All right, let's see if we can think about more problems that kernel density estimation has. So here we were discussing if there are sharp features. Let's say that the true density looks like so. So it's a one-sided exponential decay. And we're drawing samples from this. Yeah, so we're getting many here and fewer out there. What problems can you think of if we try and do kernel density estimate here? Yes? Yeah, so the you said I get a tail to the left. So this is again this over smoothing thing, yeah, near the top. So I'm using, let's say, a very narrow kernel, but even so, I will see a little bit of a trace of that kernel in an area where the density should be 0. It's correct. Can you think of another problem? Yeah. Yeah. Yes. So as we go to the right, so let's say we have chosen a kernel that is okay for this area here to the left. Let's say we get something that looks reasonable here, but then down there, okay, need a few more samples to make the point, but still, let's say it looks reasonable to the left, and then to the right, I eventually start seeing, individual bumps. I start seeing my individual observations. So in other words, it becomes difficult to choose a kernel which is good in the high density region and in the low density region. And there is then the idea, okay, let's use an adaptive bandwidth. Let's make the kernel narrow in the high density region, and let's make it very broad in the low density region. But you see, it becomes a chicken and egg problem. We do kernel density estimation in the first place because we want to know where is high density and where is low density. And the argument becomes a bit circular. And then many recipes have been invented for how exactly to adapt the bandwidth. But I would say there's no golden bullet here. Yeah. Another thing that I have, okay, so adaptive bandwidth, but it needs a density estimate in the first place. Another issue is one that we also encountered when discussing PCA. In PCA, we were measuring the distance, let's say, between a point and its projection onto the subspace. And here, if we now do this not in one dimensions, but in multiple dimensions, then we also have this problem of how do we estimate distances in space. And if the axes of the space describe different quantities, then it's not obvious what is the right relative scaling of the axis. Yeah? And that can be a problem. Yeah? So we need proper relative scaling. Okay. So another issue is that this can become slow in high dimensions, because we always need to, it can get slow if the number of points is large, because we always sum over all points. It's not the fastest technique around. Okay. And if you want to read up on these kernels, on the kernel density estimate, there is a nice script by Bruce Hansen. It is called Lecture Notes on Nonparametrics. And these lecture notes give not just the expectation, but also this variance argument that I mentioned. Okay.